Alrighty, good morning. Well, hopefully PA2 is coming along or finished at this point. Had a bunch of emails from people yesterday who I pointed to office hours, and I had one person in office hours this morning, so we got to spend time working on their code, and I think that was useful. But that's really, your best chance if you want help with anything in this course, right? Catch me in my office, because we can do a lot working one-on-one, right? I can try to give you more focused guidance than what's available in class. So take advantage of that. All right, questions up to here. All right, well let's continue looking at ODPs. Question: what does conditional jump or move depends on uninitialized values mean? So that's when you're using a typically a field inside a structure that you haven't initialized. And the most common case of that is not setting up the next field to be null if you want it to be null. Most times when you call malloc, the values will be 0 by default. That's not guaranteed though. But if you want a pointer to be null and you don't set it up, chances are your code will look like it's still working. But valgrind will take note of when you actually assign a value to that field, and if you don't make that assignment before you use it, you get that error about uninitialized values. So make sure, in particular, when you create a node, give the next field a value if you want it to have a value. And most common, this is happening in the sentinel node. In your init function, you create a sentinel, set the next field equal to null. Do that explicitly. Alright, what does free actually do? So free marks the memory as being available. It sets the valid flag to 0, effectively, from our PA1 analogy. That block may still be accessible. It may still have the old values in it that you had in it before you freed it, or it may not. It's basically setting a flag somewhere saying, hey, in the future when somebody wants to malloc something, you can use this memory location. So yeah, play around with it. Try freeing a block of memory and then doing another malloc, and see if you can get back that same block. It lets the operating system use that memory, right? It basically lets anything use that memory, including the operating system. It marks it as no longer being in use. Whereas once you say malloc, there's structures that are updated to say, hey, don't give this block of memory to anybody who's calling malloc because somebody's already allocated it. And for PA1, it was just, a valid flag that we used to say, hey, this element in the array is in use. Memory is one of those pathways to understanding how a computer works. I had a friend, Jimmy, well, I still have a friend, Jimmy, who, when we were undergrads, we were trying to understand this large computer that, the school used for classes. We were trying to understand how it worked. And somewhere in his brain, he got down, if I can understand where this one register, called register 0, where that's actually implemented in hardware, I can figure out the whole system. And we tracked that down, and we found R0, and from there we kind of, were able to work with the entire hardware of the system called a VAX 780. Memory is a way to do that with operating systems sometimes. It's like following the money in a movie, right? Follow the memory. Figure out, when I say integer I, what does that do? Where is I stored? How do I access it? or when I malloc, where is that memory coming from? Where is that physically stored in that bank of DRAM that I have inside my laptop, right? And how does, setting I equal to 7, where are those 3 1s for the 7 stored in the physical stuff, inside my machine? That's an interesting path of exploration to go down when you have time, if you want to get deeper into kind of, what's actually going on with this stuff. I think that can be a good pathway. Must have taken a long time. Yeah, I had a lot of time back then. So, yeah, that's good stuff. Alright, so we are running ODP 209 right now. So let's take a look at this ODP you just did. So that was your build function. You were building a linked list by piecing together nodes. So here's a non-stylized, poorly commented version of ODP 208. The usual struct node definition, the prototype you were given in the assignment, and as I suggested, set up 3 nodes. I call them N1, 2, 3 instead of X, Y, Z. Allocate space for them, because they each need to, actually refer to viable memory locations. Save the data fields, because we've got to, make each of those nodes have that appropriate value, X, Y, Z. And then connect them all together. So Sentinel points to N1. N1 points to N2, and so on. And then N3, the last node, that should point to null. And then return the address of the Sentinel node, which is just sent. And you want to start, being at the point where seeing this means this, and seeing this means that. Right? You're looking to make that connection, which only comes from playing with it and messing with it and getting confused about it and then working through that confusion. Right? So keep drawing pictures. They don't have to look like this, but draw pictures of what you're trying to do, write code, and try to make the connection between those. Because as we get into more complex structures, it's going to be harder and harder to actually understand what's going on by looking at this. It's going to be harder to write your code and debug your code by looking at this. You're going to want to go back to that. Alright, so today's ODP, you're writing an edit function. So edit is supposed to delete a node from the middle of a linked list. So you are given a pointer to one node right here, which points to a second, which points to a third. And your goal is to remove this middle node. So use the pointer to find this node, use that node to find the node that follows it, and then basically set the pointers next to this thing's next. And you can free this middle node if you want. I don't think I checked to see if you free it or not. The trick to this is you're not given, this middle node or this third node. You're only given a pointer to the first node. So you have to follow the links. All right, somebody freed it. Did you get full credit when you freed it? Hopefully that doesn't crash it. Yep. Okay. Cool. So yeah, go ahead and free it just for good measure. So that's 209. You free the memory in your test bed? Nah, I don't. I don't think I do. Let's see. Yeah, I do not free the memory. So when a program exits in Unix, the memory gets freed by the system. So it doesn't actually use up memory once the program terminates. All of that allocated memory gets freed. Because it's really not just one block of memory, right? When a process starts, there's memory that in some sense is allocated to that, and more can be added to it. But there's process level housekeeping being done for management of memory. Yeah, and on some systems, you know, if you don't release memory, that memory is in use until the system reboots, basically. But Unix frees it up, I'm pretty sure. Windows and most operating systems, I believe, take care of that for you. All right, cool. Any questions on any of that? All right, let's talk back about stacks. So we introduced stacks and queues yesterday. We looked at some uses for them. We talked about differences. And so what's the let's see, my only question is just kind of further understand Valgrind. So understanding what about Valgrind? So if you want to use it, basically you just Valgrind and run your program, you know, Valgrind PA2 or whatever to run it. But then there's understanding the errors that come out of it. And yeah, we have some videos where we played around. We deliberately introduced several different kinds of errors and looked at Valgrind. Big hint, remember, compile with a -G switch, and Valgrind will give you very specific information where these errors occur. So it'll say, you know, there's an error at line 17 of add.c where you're using an uninitialized value. And you can go right to that line in your file and see what you're doing, and that's usually a big hint to where the problem is. So yeah, check the videos and then catch me in office if you don't figure it out. You can leave G in your make files. That's fine. I have no problem with debug symbols. Yeah, if you compile with -G and you run Valgrind and there's a problem, it will give you, you know, information that refers to specific lines in specific .c files, and that helps you find where the problems are. Yeah, -G is a good switch. You can almost use it, you know, all the time until you're ready for like a production quality run, because it does make the image bigger and it slows things down a little bit, but you know, there's hardly any reason not to just compile with -G. I certainly, you know, have it as an option. All right, so stacks. We know the basic idea of stacks, right? So what's our four-letter abbreviation that goes along with stacks as opposed to queues? Oh, what's the four? There we go. LIFO, last in, first out, and then a queue is a FIFO, first in, first out. So last in, first out. We want the most recently added thing to be the first thing that's removed. So, and remember our functions push and pop. I'm not going to worry too much about init, is empty, is full, and so on. I just want to think about pushing and popping. So we can push n, or we can say pop. If you've done 270, the pop instruction is kind of weird because it doesn't return anything. It just removes something from the stack. But we're going to think of popping as two things. Remove this thing from the stack and tell me what the thing was that you removed. So I'm going to think of pop as returning data value. and we want these to be, you know, opposite order. Pop the most recently pushed thing. So we could implement a stack as a list and start it off as an empty list. And let's say we want to push 5, we want to push 2, we want to push 17. So what we're going to do is insert n at the start of the list. So we're going to treat push as an add function, but it's always going to add in the beginning of the list. So when I push a 5, what's going to happen? I'm going to create a node with a 5, and that's what the sentinel is going to point to. So my sentinel will look like this. And then when I push a 2, I'm going to create a new node somewhere with a 2, and I'm going to put that in the beginning of the list. So the sentinel is going to point to my 2, and 2 is going to point to the 5. And then I'm going to push 17, and that's going to create a new node somewhere. And I'm writing these at kind of random places on the page because they don't have to be sequential in memory. And our insert in the start is going to say, you know, have our sentinel point to the new node, have the new node point to what the sentinel was pointing to, which is the 2. And there's our linked list, which is a stack now. So how do we pop? Return the value of the first node, what I'm going to call a data node, so not the sentinel node. Return the value of the first node and delete that node. So when I say pop, I'm just going to look at the sentinel node, I'm going to look at the first data value, and that's going to return a 17, and I'm going to say delete that node from the list. So how do we delete? Change the sentinel to point where that deleted node is pointing, and then call free. So this goes back into the memory pool. And if I say pop again, I'm going to return the value the sentinel is pointing to. That's going to be my 7. And I'll change the sentinel to point where that node is pointing, which is the 5. And this goes back in the free memory pool. And now let's say I want to push a 99. I'll make a 99 node. I'll change the sentinel to point to that new node and have the new node point where the sentinel was pointing. So now this is our stack. So the last thing that gets pushed is always sitting right here after the sentinel, and that's going to be the first thing that gets popped. And the 5 that I pushed very first is sitting here at the end of the list. So I can pop once more, and that'll return the thing that the sentinel is pointing to, which is a 99, and it'll change sentinel to point where 99 is pointing, which is back at the 5. And then return this to the memory pool, and now if I do one more pop, the sentinel is pointing to a 5, so a 5 gets returned. Change the sentinel to point where node 5 is pointing. Well, node 5 is not pointing anywhere, it's null. So this next field becomes null, that goes into the memory pool. Does that make sense? Everybody believe this is working like a LIFO? And this is really, you know, our stack of plates, right? And this is the top where we put new things in, and this is the top that we take things off of. All right. Right now, you know, we've popped the last thing from the stack. The stack is empty. How do we know that the stack is empty? Because the sentinel's next field is null, exactly. And this is also how we know when a linked list is empty. If the sentinel points to null, there's no data in the list. The list is completely empty. That's what an empty stack is. So we could actually write our isEmpty function. So if stack next is null, we could return true, otherwise we return false. If we're doing this in C or Java, this is legal. All right, it's a one-line function. Just return the value of this conditional statement. If we do that in Java, it'll return a Boolean. C, it'll just be a 0 or non-zero. So isEmpty is easy. IsFull is harder. There's no way when you're building a stack using a linked list to tell if the stack is full, because that basically means there's no memory available, and that's a hard thing to detect. You could try to malloc a block of memory and see if it succeeds, but that's not really valid. Running out of memory is not a normal condition, right? So it's something we just kind of detect when we try to push. Now, when we do our push, we could return a flag saying, were we successful in pushing? And remember, when we push, we're inserting a node, so the first thing we're doing is making a new node. Well, we can check to see if that creation succeeds or fails. To create a new node, we have to call malloc. We can see if malloc returns null. If it does, then we're out of memory, and we can have push return a 0 saying, hey, I wasn't able to push this. Otherwise, take your new node, insert it in the beginning of the list, and return, you know, a 1 saying that we did push. And pop is supposed to return a data value. If you call pop on an empty stack, what should you do? It's hard to say. Because it's already returning a value, we can't really return a flag as the value of the pop function. But if you try to pop from an empty stack, what are you going to return? Ideally, you'd like to somehow tell the user that an error occurred. So you can trust the user and just assume, you know, that they're going to make sure the stack's not empty before they try to pop. Or you can, like, you know, throw an error that causes the program to crash. Or you could, you know, pass an argument to pop, which is an error flag, and you could adjust that, and so on. Those are implementation details. High-level implementation details. All right, so this is a basic stack setup. And terminology that will be useful going forward, top of stack. So we usually think of stacks, well, I guess, we usually think of stacks as, you know, a pile of things, and we add things to the top and we take things off from the top. And so we have this terminology for top of stack, which refers to the thing that you're about to remove. It's the action end of the stack. And the bottom of the stack is the stuff that's way down in there, this 5 that I pushed, and then pushed a bunch of other things on top of. But top of stack shows you the end, you know, where you're about to remove from. And this gets more interesting when we implement stacks differently, using arrays instead of lists. But linked list, easy way to do this. All right, we can also implement queues using a linked list. So queues our two functions are insert and remove. And same idea, but we're going to insert at one end and remove from the other. By the way, what's the efficiency of this? Does our push and pop get any slower as the stack grows? If we have a stack with 3 things in it, or we have a stack with 3 million things in it, does it take any longer to push or pop? Stays the same, right? Because it's a fixed set of operations. Go to the Sentinel, make a new node, have that node point where Sentinel points, have Sentinel point to the new node. Nothing to do with how big the stack is. And that's useful. That's something we want, because we don't want to get something that gets slower and slower as we put more and more data into our structure. So we want to preserve that behavior with the queue. Okay, so the queue, we're going to insert at one end of a list, and we're going to remove from the other end. So I'm calling my Sentinel node queue here. I don't know if this is for PA3. I haven't decided what PA3 is going to be. It might be stacks and queues. It might be hashes. Yeah, I might do both. Because I'm not going to post it for another week. So we got time to get through some stuff. And yeah, maybe I'll do a hash of stacks and queues or something. All right, so basic idea would be, you know, if this is the stuff in our queue, remember we insert at the tail and we remove from the head. That's just terminology. The head is the end from which you remove, the tail is the end into which you insert. So we could do this by you know, inserting something by putting it in the beginning of the list, and removing by taking it off of the end. So we could treat this as the tail and treat this as the head. And so you want to insert something into the queue. Well, same thing we did with pushing in the stack, right? Just make a new node, squeeze it in right here after the Sentinel. That's easy. And as we do that, right, effectively we're preserving the order in which things are added to the list. Right, we pushed a 5 and a 2 and a 17, 5, 2, 17. That order is preserved. It's just that in a stack we pull things off in the reverse order. In a queue, all we have to do is pull off from the other end of the list. So if we wrote our insert, just squeeze a new node in here, and then our remove to just give us the last node, that would implement a queue. There's a performance issue with this, though. To remove the last node, I've got to get to the last node. which means I've got to go boink, 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 all the way down my queue until I get to the last node. I've got to remember what the previous node was, and then I can delete this last node, right? Return that value, make this previous node the last node by setting its next to null. That's an efficiency problem, though. So I could try to get around that. By having a pointer, I'll call it last pointer, that points to this next to the last node. And then I can just, follow this to here, set this thing, return that data value, release that from memory, change this to be pointing to null. But I've still got to change last pointer now to point to what's the new, next to the last node. And to find that one, I have to start from the beginning and go through. So a doubly linked list can work here. Right, if each node has a back pointer, then we can just have a pointer to the last node, and when we want to remove, we can grab that data value, use the previous field to find the address of this node, update last pointer to point to that, and then release that node. So doubly linked list, we can restore our behavior. But with a singly linked list, we can still make this work in order 1. Any ideas how? This is subtle. So the trick is adding to and removing from a linked list are fundamentally different operations. When we remove a node, we need to know what the node is before it in order to adjust its pointer. And if we're removing the last node from a list, right, we need some way to get to the next to the last node so we can change its pointer. But if we remove the first node from a list, that's always easy. We know what the previous node is. It's the sentinel. So if we simply change this around and we say let's remove from the beginning of the list, so make this the head and make this the tail. We could make last pointer a stack. That would be a cool workaround. Because then we could push the addresses of these. Yeah, that would work well, actually. I wonder if that's actually a mutated version of making a doubly linked list. It might be. That's a cool idea. Alright, so if we put the head of the queue over here, remember the queue is what we're removing from, the tail is where we're inserting. And if we actually make, a variable called tail that we preserve between calls that always points to this last node, we're back to order 1. So to insert, we basically create a new node and we jump over to tail, we say tail next should now, refer to our new node. New node next should be null. And we change tail to to be the address of this node we just inserted. And now if you want to insert another node, well, you make a new node. You go to tail, you set tail next to B, pointing to the new node. You change the value of your tail variable to be the address of this node, and you set tail next to null. So inserting is order 1 no matter how big the list is, and removing from the head, that's still order 1 because that all happens up here. Right? Take the node that the sentinel points to, pull off the value, that's what we're going to return from the remove function, change the sentinel to point where that first node is pointing, and then free that memory. We don't need a variable called head because head is always Q arrow next, but we could have a head if we wanted. So to make a queue with a linked list, we have two functions, an insert function and a remove function. We insert at the tail, which is the end of the list. And we remove from the head, which is the start of the list. And those give us nice efficient operations. The isEmpty function is still just seeing if the list is null. So if the sentinel node's next is null, then the queue is empty. And again, queue full, we don't really have a reasonable way to check that, because that just means there's no space left to make a new node. And sometimes, you know, we have other functions. We could have a peek function, which says, you know, don't remove anything from the queue, but tell me what the next value is that's going to be removed. And that just, you know, returns tail arrow data. And for a stack, we can do a peek function, which just returns, you know, sentinel arrow next arrow data if the stack's not empty, or some kind of error condition if the stack is empty. So that's basic stack queue. That's really all there is to it if you want to build these using lists. So questions about that? All right, let's talk about implementing stacks in hardware. And that's a little bit of a weird thing to say because all of this stuff is hardware, right? When you write a C program, at some level, you know, your program is a bunch of transistors or capacitors in a memory driving, you know, multiplexers in a big state machine made out of logic gates. I mean, at some level, it's all hardware. But let's think about at a lower level. How many people here have had Engineering 270? I should get this number from you. Go ahead and raise your hand if you have, just so I can see like a tally. If you've already taken Engineering 270. And it's not a prereq for this course. It helps sometimes, and I'll refer to things from there. Let's see. All right. several people plus one who doesn't know how to raise their hand in the participants window. Okay, that's cool. You can put your hands down. So about half the class. I've had students who take Engineering 270 first, and they tell me that helped a lot with CSE222. But I've had students who take CSE222 first, and they tell me that helped a lot with Engineering 270. So I don't think there's an inherent advantage to, you know, taking one first versus the other. I think they really kind of help each other. But some of what I'm saying here, I'll refer to 270 sometimes. But if you haven't taken that, just make a note, and when you get to 270, it may come back. So 270, you know, we deal with assembly language, which is the lower level language that we compile things into. But we also deal with the hardware of a computer, right? How does the actual physical stuff treat your assembly language program to, you know, execute your code that you might have written in C? Oh, the traffic light, yay! Yeah. Oh, that could be PA3. I could have you no. So inside a computer, right? There's a CPU. It's processing instructions. They're low-level instructions, ones and zeros, and there's a memory that holds the instructions, but also holds the data that's being manipulated. Most CPUs and instruction sets also have support for a stack at the hardware level. And so this is stored, you know, in memory, like most things. So here's your memory. And there's a register, which is just a variable that the CPU keeps track of, and it's called a stack pointer. Usually just SP. That's actually the register name in a lot of implementations. And SP is a pointer to memory. It's got some value, you know, 7FFF, FE84 or something like that. It refers to some memory location. And typically, this location is considered to be the top of a stack. And when you ask the CPU to push some number, let's just say it's N1 onto the stack, here's what it does. It takes this number N1, it stores it in memory. Where does it store it? Wherever SP is pointing. So if SP is pointing right here, pushing N1 would say just put an N1 in this location in memory. And then decrement the stack pointer. So now the stack pointer points to this previous location, which is now considered the top of the stack. And then if you want to push N2, that would look at the stack pointer. It's referring to this location. Let's push an N2 in there, and let's decrement the stack pointer again. And now this is the top of the stack. And we'll do one more push. So stack pointer is right here. That's where N3 gets stored. Stack pointer gets decremented. This is the new top of the stack. And then popping, we just reverse that operation. So popping in this setup, we would have to look at the stack pointer. We would need to increment it. So change the stack pointer to here, and then give the caller back the value at that location in memory. And then if you do another pop, do the same thing, increment the stack pointer, give the caller back this location. So the first pop will return the value N3, the second pop will return the value N2. Now if we do another push some new value N4, what do? We store that where the stack pointer is, which is right here, and we decrement the stack pointer. So our stack looks like this. There's an N1 at the bottom of the stack, there's an N4 at the top of the stack, and the stack pointer is pointing here. And this is effectively doing the same thing as we did with a linked list. Except with a linked list, we kept changing, we kept creating new nodes and having them point to next nodes. With a stack in memory, the contents of our stack is stored sequentially. But we changed the notion of where the top of the stack is by adjusting this variable that we call a stack pointer. And notice that, even though I popped off an N3, it's still sitting in memory. It's not considered part of the stack. I'm never going to get that N3 again by saying pop. Because if I say pop right now, it's going to give me N4. If I say pop again, it's going to give me N1. If I pop after that, it's going to give me whatever's in this location, which, I don't know what that is. But it'll give me whatever's in that spot. And so our stack is never really empty. But if I keep popping, eventually I might get to a point where I try to access some location I don't have access to. And then I'm going to get a really bad kind of seg fault. Alright, so this is more like a hardware stack. We can mimic this behavior in our own C code because arrays are really just like miniature versions of memory. That's probably worth tagging. Right? If we have an array that we declare, say, an array of integers, we could have stack pointer be an index into that array, right? And maybe store, index 0, 1, 2, 3, 4, increment instead of decrement when we push. And we could mimic the same structure. And there's details here. This is still kind of high level view. There's details. The way I've drawn this, when you push, I'm decrementing the stack pointer. That's probably the more common approach, but we could just as well have said, when I push, I'm going to increment the stack pointer, and my stack is going to grow to higher locations in memory. When you do system programming, this will drive you batty at first. As far as, when the stack grows to a higher location, is it a smaller address or a bigger, and so on. But, the stack could grow in this direction, or the way we've done it here, it grows actually in that direction. It's the pile of plates with, gravity down. We also said, let's save our value where the stack pointer is and then decrement the stack pointer. We could choose to decrement the stack pointer first. We could say, okay, when you want to push, first I'm going to lower the stack pointer value, and then I'm going to store at that lower location. And then when we pop, we would want to look at the value at the stack pointer before we increment the stack pointer. So there's at least 4 ways to implement a push instruction. Pre-increment, post-increment, pre-decrement, post-decrement. And they're all stacks. They're all valid push operations. And it doesn't really matter too much as long as you're consistent. But there's reasons why, most systems use a stack that grows to lower addresses rather than larger. and pre-increment, post-increment, it changes your code. But again, as an abstract data type, we don't care. If we were writing a program that's calling push and pop, we don't really care how that's being implemented. All right, so we'll push this out into an array tomorrow, and we'll look at some C code to manipulate a stack stored in an array, and then we'll go ahead and we'll switch over to queues, and queues are going to be kind of a different beast. And then we'll go on and we'll look at some more specific applications of these concepts. All right, have a good one. I will see you next time.